Yeah, good evening, everyone. You're able to hear me, right? Can anyone just unmute and tell me whether you are able to see me and hear me? You can type in the message box if not. Yeah, thank you. We'll wait for like a few more minutes, maybe 3 or 4 minutes. We'll just see if someone else wants to join. Then we'll wait for 2, 3 minutes and then we'll start the session. Yeah. Meanwhile, you can introduce about yourself. Which year you're studying, BTech or MTech, and which college you're from. You can just simply type in the message box. Okay. Yeah, we'll wait 1 more minute. Some people are joining, so we'll just wait for them. After that, we can start our session. Meanwhile, the person, like the candidates who joined just now, maybe they can introduce about themselves. Yeah, I think now we can start. So everybody can I just want to confirm again. You can see me and you can hear me, right? And I think I think my screen is also visible to all. Just press yes if you can if you can see that. Yeah, thank you. Yeah, thanks a lot. So welcome to the online session for this NPTEL. The course is Structural Analysis 1. This is basically an undergraduate course. So today I'll be taking some tutorial classes. Yeah, just excuse me because in between maybe some people keeps joining, so I need to just go back and I need to admit them. So maybe in between, if I go there, just please excuse me for that. So This, if you are not able to hear me, or if you have lost me or something, someone can unmute and just tell me, because you know, this I feel it should be more of a two-way thing, so that, you know, maybe I'll have some interaction also with you. So let us start. So this is basically on the week one, like whatever the course content was there in the week one of this structural analysis one. So I'll be basically taking some tutorial, some problems which I felt those are kind of interesting, and also some problems I have taken from the book by R.C. Hibler. So yeah, and I am Prithvi Sangani. I'm a research scholar. So I'm a PhD student. I'm from Department of Civil Engineering. I'm basically from IIT Hyderabad. So that is all about me. And you can see my email IDs. So in case if you have still some doubts, or if you want to clarify something else, maybe you can also email me regarding these tutorials. And if you have some other doubts basically from this subject, you can always contact me. So I think now we are good to go. If you have anything, like any clarification, if you want some clarifications, you can ask me now. Or everything is fine, we can just start with the tutorial now. Can someone message me if you want some clarifications, or maybe if you have some doubts, you can just ask me now before we start. Okay, okay, thank you. So the first, I think this week's course content is more of a basics. Actually, it's more about a revision of the engineering mechanics, and more of strength of materials, which you might have already had some idea about. So this tutorial again has the similar kind of questions, some basic questions, but some questions are a little interesting. So maybe we can just go through those questions. uh, I hope you can see my screen. So from now onwards, it's better someone unmute and just tell me yes or no, because always I need to keep coming back and seeing this message. So if someone is okay with it, they can just unmute and they can say, they can just come back. So sure, thank you, thanks a lot. So this is the first question. Sorry, someone came in. Yeah. So this is the first question. Uh, this is again basically the question is the girder shown in this is a girder, like, you know, you can see this is kind of an I section. So the girder shown in the figure below is made up of a concrete of density 2400 kg per meter cube. The six reinforcing bars are of diameter 20 mm each and has a density of 7850 kg per meter cube. Determine the dead load of the girder per meter length. So they are asking for per meter length what will be the dead load. All the dimensions in the figure are in mm. Consider acceleration due to gravity is 9.81. So you can also start calculating with me. So it's actually the same question. So you can see whenever you are planning to do anything, right? So will have a lot of loads, which we consider dead loads, live loads, and also this is one part of thing in which we usually try to calculate what is the dead load applied. So dead load is actually, it's obviously the self weight. One component of the dead load is self weight, and also one component will be the load which permanently exists on the on the structure. So right now they are asking us to calculate the self weight of the beam, right? So now the beam has six reinforcement bars, okay, and also it's an I section. So just calculate the area multiplied by the unit length. They are asking for the unit length. So we'll just calculate the area of this section, this complete section. We'll calculate the area of this. We'll multiply it by 1. Okay, so you can divide this, maybe, you know, this is a basic level thing, so you can just divide these things into different parts, and you can just calculate the cross sectional area, and you just multiply it with 1 meter. You will get the volume multiplied by the density will get the weight of it. So we also have two different components. One is the concrete, so the concrete component is this, and we have the steel. So we have steel component. So we, for the steel, they have defined what is the diameter of the bars. So let us just go ahead and let us start working on this, right? So what I'll do is this part, this rectangle part, I'll mark it as 1. This trapezoidal part I'll mark it as 2. This complete rectangle part I'll mark it as 3, and this is 4, and this is 5. Okay, and let us say the reinforcing bars are like like we can calculate the volume and then weight of the reinforcement bars. So let us say the the dead load of the reinforcement bars. What is the dead load of the reinforcement bars? Can someone just calculate the area and just let me tell me what is the complete area of the reinforcement bars? So we have how many bars do we have? We have 3 bars on the top. So, bottom reinforcement is 3. So we have 6 bars. Okay. The area of cross section is pi by 4 into d square into they're asking us to calculate per meter length, right? So per meter. So let us say I'm taking it as 1000 mm. So I just want to calculate everything in terms of mm, and then I'll convert into the uh, the metric system. So 6 into pi by 4 into 20 square into 1000. This gives us the volume. If someone already calculated, they can just tell me the value. If not, I'll also calculate. Yeah, did anyone get the answer? This is what I got. Maybe can anyone confirm whether this is correct or not? Yeah, thank you. So this is the volume. We need the weight. So weight density of steel multiplied by volume. Let us just do that. This is mm cube, right? So now what I'll do is I'll just convert into meter cube. 10 to the power how much? I need to this is 10 to the power 9 because millimeters are 10 to the power minus 3 meters. 10 to the power minus 3 whole to the power 3. So they're 10 to the power minus 9. This multiplied by what is the density? Density is given as 7850. Let us just make this. So what I'll be getting? 7850. Oh, yeah, 7850 divided by 10 to the power minus, yeah, yeah. This is what I'm getting. 14.797. Okay, okay. This is in kgs, right? So I need weight. I'm asking about the weight. So this is the mass, right? So usually we see mass and weight usually we'll be using interchangeably, but we have to be very cautious when we are dealing with weight and mass. So what is weight then? What weight will be? Weight is equal to 14.797 multiplied by acceleration due to gravity. So that is 14.97 into 9.81. This is like 145.16 Newton. I can also write it as 0.145 kilonewtons. So this is about the steel. I hope this is clear. I think you also got the same answer. Someone was responding to me earlier. Who's that? Oh, yeah, I think fine. So let us now sorry, I didn't get you. Yeah, okay. Let us just continue. So we have uh, let us say now the volume of one, that is equal to, I'm directly calculating the volume, 200. This is one, okay. This part is one. 200 times 400 times 1000 because we need it per meter, right? So 1000. uh, Actually, if we want to be very precise, right, we need to deduct the volume or the weight, the volume of reinforcement. But let us just take this value also. We'll see if this is not satisfying much. I don't think that will be a big thing because the volumes are very low. You can see here the volume of these reinforcement bar is about 1.885 into 10 power 6. But when it compared to the the area of cross section of this uh, concrete, the volume of the area of cross section of the steel bars are very less. So I think that is like, within 1% or maybe 2-3%. So we'll just consider it. We'll see what happens. So this is area of cross section. This is the length. So what we'll be getting, 200 into 200 times 400 times 1000. So this is almost like 10 to the power 0.08. So what I'll do is I'll directly calculate the weight also. So what is the weight, then multiplied by the density, 2400 multiplied by G, that is 9.81. So this is in mm, this is in kg per meter cube, this is in meter per second square. So this mm cube has to be multiplied by 10 to the power minus 9. Can someone say what is the answer? 1000 divided by multiplied by 2400, 0.81 minus 9. How much is it? Can anyone say? 1.88 into 10 to the power 3. This is newtons, right? So yeah, fine. Yeah, thank you. I got the same thing. Same thing. 1.883 something like that. Yeah. The next one. So the trapezoidal, the area of cross section of the trapezoidal. So what is the area of cross section of trapezoid? Half times the height. So that is 150 times. This is 150. This is 400, and this is 200. So 400 plus 200 multiplied by 1000, and the same thing, 2400 0.9.81. Yeah, can anyone say what is this? 150 divided by 2 times 600 times 1000 times 2400 times 9.81 10 to the power minus 9. Yeah, just tell me whether this is correct or not. Is it right? Yeah, thank you. So weight of 3, this section, this one. So this is 200 times 500 times 1000 times 2400 times 9.81 times 10 to the power minus 9. How much is this? 200 times 500 times 1000. Something like this, 2.34, something like that. Okay, thank you. So weight of 4, that is similar to weight of 2, that is 1.059 times 10 power 3, and weight of 5 is similar to weight of 1, so that is 1.88 times 10 to the power 3. So all in all, how much is this? W1, W2, W3 weight of concrete, that is equal to 1.88 times 2 plus 1.059 times 2 plus 2.35, 8 point, yeah, 8.23 kilonewtons. Weight of steel we already found out, that is 0.145 kilonewtons. So plus 0.145 kilonewtons, 8.37 or something like that. So total weight is 8.373 kilonewtons, something like this. Which is what, which is nearby. And now you can actually appreciate why the value is little higher when compared, because in this we already included the area or the volume of the reinforcement. If we actually deduct this, right, like let us do that now here itself. So this already contains the the weight of the volume of this. So if you just deduct that volume in this, that means you have this volume and you have this cutout volumes, 1 2 3 4 5 6 cutout. So maybe for that you will get exact answer, the accurate answer of 8.34. So see, in this actually gives us a very basic fundamentals of how to calculate the dead loads of the dead loads usually which comes on the structure. Second thing, you can also appreciate the weight of the concrete. When we say RCC structure, right? So the weight of the concrete is too large. You can see what is the percentage weight of the steel? It is like 1.145 divided by, let us say, 8.34. Yeah, the percentage of the steel is like only 1.7 percentage, you can see. So 1.7 percentage of weight is only steel. You can you just think of this. When we say RCC structure, the steel is actually of a very lower, the percentage is very low, but it plays a very vital role. So that maybe in the coming, maybe in structural design or the RCC design, you can actually find out how the steel plays an important role in the design of the structures. So I hope the problem one is clear for all. You can just say yes, or you can just message okay or yes or something like that. If you have some doubts, you can just tell me. Can anyone respond, or shall we go to the next problem? Okay. Yeah, thank you. Oh, sure, thanks. Okay. This is a basic one. I just want to, I just took this problem just to understand what are the different types of loads coming onto the structure. So this is one part of a dead load. We also have live loads. We have wind loads, earthquake loads. We have snow loads. We have impact loading, and so on and so forth. So this is one type of the load which usually, actually this is the most, when we design a structure, dead loads, the civil structures usually, those are heavily built, right? So the dead loads actually make a very high good proportion of the total load. So yeah. Now let us go to the second one. So this is about the stability. I just want to talk something about the stability of the structures and also the indeterminacy. Okay. So if you see the first one, so what do you think of what is this structure? Okay, I'll just name it as A, and this is B, and all these things are, this is another one. Let us say this is 2i, 2 1, and this is 2. So when you just think about this, the first one, 2 1a, uh, you just tell me whether it is determinate structure or indeterminate structure. I'll just write the reactions also. This is a roller support, right? So roller support will have the reaction this way, the other reaction this way, and the reaction in this way. So we don't have any the lateral restraint from the roller support, because if you just push this specimen, it will just go off. There's no restraining. So what do you say? Is it a determinate structure or indeterminate structure? Can you please? Sure. I'm sorry. Yeah, now you're able to see it, right? Fine. So tell me whether this is determinate structure or indeterminate structure. Oh, fine. Can anyone comment whether it is stable or it is unstable system? This picture. So now we have P as an inclined force, right? Let us actually have some. Let us have the components of this. So what is the horizontal component? So this is horizontal component, and this is the vertical component. So you have vertical component. You have vertical load coming here. For example, what if this horizontal load is applied to this beam? So you have an horizontal load applied this. There is nothing to resist that force. There is nothing to resist this force. There is nothing that which is resisting this force. That means this is like a skateboard or something like that. So you have this is something like skateboard. You will just push this in this way, and this keeps going like this. So that is not a stable structure, right? You know, the structure is actually something which should actually listen to your loads, your type of loads. It should actually, if for example, if you're loading something, let us say this chair or table, it has to actually take that, you have some requirements, so it has to follow that requirements. For example, if you are keeping something on it, that means it has to stay still. Right now I'm keeping the laptop on this table, so the table should be stayed still. We don't expect it to just move away, because that is your requirement, right? So the requirement of the structure is, it has to carry the loads in such a way that, we wanted to have in certain way. But in this, it is not like that, right? It is, if you are loading, okay, what if you are just loading in this direction, then it is fine. But what if you are not loading in that direction? If you're loading in horizontal direction, then it is gone. So yeah, yeah, sorry, actually someone just joined. So if you are loading in horizontal direction, that means it just moves off. So this is unstable system. This is unstable system. So when it comes to this, again, this type of loading, you can see, again, this is a roller here. This is a roller support. This is again a roller support, and this is a roller support. So what do the roller support actually have? It can't move in this direction. That then it will resist. Then you will have a resistance coming here. You will have a resistant force coming here. It can't move in this direction. In this direction it can move, but it can't move in the bottom direction, in the downward direction. So when you are restraining its movement or its deformation in some direction, there you will have a resistive forces coming in that. So that is how the reactions generate. And for example, it can move in this direction. So if you just push it, it will just go in this direction. You will not have any resistance coming from this direction. But if you are trying to push this in this direction, then you'll have a resistance. It will not move. Then it will give some resistance, right? So okay, all right. So now what I'll do is, we'll have this direction. This is the direction, and this is the other direction. So what do you mean? Like for example, uh, when do you call that the system is in equilibrium, right? So we can call the system is in equilibrium when we have forces in all the direction. Let us say this is x force is 0, forces in y direction 0, forces in z direction 0. For example, the forces are not 0. Let us say in this case, this is a bar. I'm pulling this bar with 5 kilonewton load, okay, and from this direction I'm pulling it with 3 kilonewton load. So what happens to the bar? So 5 minus 3, the forces are not balanced. That means in this direction, you will have a net force of 2 kilonewtons. Because of this net force, this bar will keep moving. This bar will keep moving. And let us say the mass is like m, and it will accelerate actually. It will accelerate with the force of 2 kilonewton by mass m. Right. For example, if I want this to be in the state of equilibrium, so we have this tug of war kind of game, right? So let us say no one is moving, okay? So one group is pulling this in 5 kilonewtons, they are pulling this towards the right side with 5 kilonewton load. The other group is pulling equally with 5 kilonewton load. Then no one wins or no one loses. They'll still stand at some place. If the group here, they again gain some strength, and they'll try to pull this by 6 kilonewton load. Everyone has, kind of, they'll take some reaction from the ground. You can see that, right? They'll take some reaction from the ground and they'll keep pulling it. Then you have a net force of 1 kilonewton, and this entire thing comes this side, and they'll, these guys will be winning. So that is where the equilibrium stands here. In this, it is only about uh, summation of the forces being equal to 0. And also we should have the summation of moments should be 0. Okay, so let us say why the summation of the moment should be 0. Let us say I have a pin, or I have let us say there is some, let us just take the fan itself. This is the the wings of the fan. So I'm just pulling this, or I'm just rotating this in this direction. what happens? It will just keep rotating. It will keep rotating. It will keep rotating. So what if I'll have a fixed support. I'll just hold this pen like this, and I'll then do this. So now because of this fixity, it will not rotate, right? It will actually have some reaction coming here. So for every system, you should always have this thing satisfying. Moment, summation of moments, and summation of this should be here, irrespective of whatever you are doing. For the stable system, I'm talking about the stable system. So let us say this system, this has this vertical component. I mean, this is the inclined component, and this is the vertical component, and this is the inclined component. So I have some load, there is some load passing like this, or maybe a point load somewhere here. So what I'll do is, irrespective of the position, usually we have habit of taking moment about A0, moment about B0, or moment about C0. But that is, that is for easiness of our problems, right? So what I'll do is I'll take some moment where all these three intersects. Let us take this point, okay? Let us say take this point. For the system, like I said, for the stable system, at any point you are considering all these things, summation of forces, summation of moments, that should be 0. So I'll take this point, some random point, but that random point now seems to be an intersection, that the all these forces where it is concurrent. That means it is intersecting at that point. So let us say at this point, will our moments be 0? So because of this load, you can say this load, let us say this is P load. Because of this load, I'll generate some reaction here, R1, some reaction here, R2, some reaction here, R3. So at this point, what is the complete total moment? This R1, this is going actually here. So there is no lever arm, right? So R1 into 0. So here it is 0, R2 into 0, R3 into 0. But let us say my load here is P into what is the distance, and this is the distance D from O. So you have P into D, summation of moments is equal to P into D plus R1 into 0 plus R2 into 0 plus R3 into 0. So that is PD. It is not equal to 0. Then if it is not equal to 0, how can you say the system is in stability? So the system is not stable. This is again the concept of unstable. Again, this is in unstable equilibrium. So to actually generalize this thing, what usually we call is when the forces, right, the reaction forces are concurrent. That means when the reaction forces are actually meeting at some point or intersecting at some point. Now this is the case of that concurrency. Then the system is unstable again. Okay. So this is about these two systems, and now you can comment about this. This is again a fixed support, and this is again a fixed support. So how many reactions do we have for the fixed support? Can someone quickly say how many reactions do we have for this fixed support for a plane member? Can someone, for the fixed support, how many reactions do we have? 3. Yes. Yeah. 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 Thank you. It's yeah. Yeah, yeah. Thanks for saying. It's better you can just unmute and tell me that there's no problem, because I should keep coming back always to this. I hope you understand that. Yeah, thank you whoever messaged me. So we have three, right? So vertical reaction, we have one horizontal reaction, and we will also have moment. Okay. So the same similarly we have 1, 2, and also moment 3. So I usually use this notations for reactions, because we'll have the same arrow mark for the loading also, right? So arrow mark, this cross, that means it is a reaction force. If it is an arrow, it is not a reaction force, it is just a loading. So usually I follow this kind of notation. So whenever I draw a reaction, I'll just draw this cross mark on the reactions. So we have 3, and how many equations of equilibrium we have here? So the reaction forces are 3 plus 3 into 2, we have 2 supports, so 6 we have. Equations of equilibrium are 3, right? So degree of static indeterminacy will be 3, 6 minus 3, that is 3. So with using these 3 equations, we can find out 3 unknowns, right? There are 6 unknowns. 6 reactions are nothing but 6 unknowns, but we only have 3 degrees of equation, 3 degrees of equilibrium. I mean 3 equations of equilibrium. that is sigma fx equal to 0, sigma fy equal to 0, and sigma m equal to 0. So about fz and m in other directions, you will this is again when it comes to the space stress, you will space structures like space frame or the space truss, then you'll be learning more about it. But this tutorial or this course is all about the plane members, which are which are in plane, which are having the same plane. So this is a pin support and this is another pin support. So you have two two supports, you have two reactions and two reactions. So 2 into 2, you have 4 unknowns. Degrees of equation again equilibrium are 3, so 4 minus 3 is 1. So this is again indeterminate with degree 1. This is indeterminate with degree 3. Can anyone say what is this? Is this indeterminate or determinate? This one, see. Maybe someone. Yeah, okay. Okay, I'll just actually, yeah, even I used to confuse. So you can see this is actually a pin support. Okay, this is a pin. So usually we'll be representing pin support as something like this, right? So this is the similar one. This is something which is similar. But here this is actually something different. This is actually a roller support. So this is something like this. This is what we usually will usually will denote it as. So now you can say, I think this is a roller support and this is a pin support. So we have 2 and we have 1. So we have 3 uh, unknown 3 unknown what do you call it? 3 unknown reactions, and we have 3 equations. So degree of static determinacy is 3 minus 3, that is 0. Okay, so this is determinate. Yeah, I understand. Actually, this is a little confusing, but this is how it is actually. In this is taken from the RCM. So this is how it is defined in the book. So he usually, I think, yeah, this is how it was defined. So again, here you can see this is a pin support. Pin support. You have a hinge here. So hinge, there is a release, right? At the hinge also we'll have an extra equation of equilibrium. So at the hinge, you can say that the moments are the total moments about the hinge is 0, because hinge is actually a hinge. It will only uh, take the shear forces, not the moments. So if you, it is like this. So for example, you can see here. Let us say this is my hinge. You can see me. I think so. If you just give some load, it will keep rotating. That means this is not taking any moment. It is taking a moment, but it is not taking bending moment, right? So this is how it is. So again, this is again a determinate structure. So you have these formulas. I think you might have seen a lot of formulas saying r is equal to 3n minus something. So I personally suggest you not to actually directly mug up those formulas, but you understand the basics behind this. In this I never used any formulas in this, right? So uh, you have the number of unknowns. You can just simply find out what are the number of unknowns, and also you also know what are the different types of equations of equilibrium, or the number of equilibrium equations which you have. And also you also have, for example, in this case, the last case, in this case you have an extra equation coming from this. So for this, you can just simply say there is 1 minus 1. So this is simply like this. So we have four unknown equations. You have 3 equations of equilibrium, and you have one extra equation, which is this hinge, giving this hinge. So you have 4 minus 3 minus 1, that is 0. So this is determinate. You can easily find out by using equations of equilibrium. So I hope this is fine. This problem is okay with you. Sorry, the C this you're saying about this, right? Yeah, this is unstable. You can see this is uh, you have, this is concurrent. That is unstable. Yeah. So in this you can see one, you have two, we have one, and you have two, right? So when you are loading, right, actually this is a hinge. This is a hinge. If this is actually having a rolling support, a roller support, maybe it will be an unstable thing. But in this case, I think there's no instability. You can see we are getting as zero. Even here it is zero, but you have this concurrent forces coming. Is it fine? So shall I go to the next one, or anyone have some clarity? Anyone have some doubts, or yeah? Shall I go for the next problem? Yeah. Thank you. Uh, Vidyadarji, actually, it's better you tell me. You can unmute and you can tell me. Okay. Even Nitya, Joy, and Sharon, Nagajyoti, it's better because I need to keep coming back and I need to check this. So please consider this as a request. Yeah, yeah. Thank you. Thank you. Thanks. So let us go to the next question. This is again this is again how to determine the uh, reaction forces on this structure. So this is a beam. We already have this beam. Uh, this is an inclined support. So we have an sorry. This is an inclined load which is acting on the beam. So this is a pin support. This is a roller support, and we are giving some bending moment on this on the end of the beam, and also we have some inclined load of 80 kilonewtons. So that with inclination angle of about 45 degrees. So how can we go about this? And before that, I just want to confirm. I just want to maybe some people might be knowing about this, but I just want to give some clarity about force versus shear force, movement versus bending moment. Okay. So I think most of you know about these differences, but just for the sake of just explanation, I'll just tell you that I'll just tell you what is the differences. So let us say the similar one, we have 5 kilonewton forces acting in this direction, and let us say I have 3 kilonewton acting. So if someone asks you what is the stress generated, let us say the cross section area is A. So what is the stress generated? Do you think there is some stress in the in this member? I think so, because you have an unbalanced force, right? So you have an unbalanced force, at the same time you also have some forces which is acting inside, right? So I'm just saying in this way that you have this is you can just divide this into 3 kilonewton, and this is 2 kilonewton. You can just simply do this. So if this is 3 kilonewton and this is 3 kilonewton, that means you are stretching also. This is undergoing some stretch. So if you cut this section here, what happens is that you are also pulling this 3 kilonewton. You have this 3 kilonewton divided by the area of cross section. So if this is 3 kilonewton divided by area of cross section, this is the internal stress. So what is stress? So there comes the definition of stress. Stress is the resistive force, right? The resistance or the resistive force. The resistive force divided by area, unit area or area, whatever it is. So only when you have the resistance coming from coming inside, right? There is a resistance coming, then you'll have stress. So pressure is actually again the force by area. That is not you just you are applying some force on a particular area. So you just multiply, you divide that area by the applied force, then you'll get pressure. But the stress is actually the resistance offered inside the body or the inside the material. So Similarly, the force also, right? You can say some force acting on it, but the shear force is actually a resistance offered because of that force. So that is the shear force. And when it comes to the moment is simply, you can say just you are applying some moment. This is actually a moment. And let us say I'm up again, same thing. You have this thing, you have a block, or you have some say a ruler or some scale or something. You are applying some movement like this. You're just trying to rotate in this fashion. So what happens, it is just placed on the table. It will just keep rotating, right? There's nothing happening. It keeps rotating. It keep rotating. There's nothing to actually stop it. It keep rotating. But when you actually clamp this somewhere, let us say I'm clamping this somewhere and I'm trying to rotate this. I'm trying to rotate like this. I'm trying to rotate like this. So in that way, in that scenario, what happens? You'll also have a resistance coming from this because you are doing this. Let us say this is this is M1. So you'll have a resistive force because I said the equation of equilibrium should be valid there, right? So when I'm giving M1 this side, this should also act in opposite direction to actually nullify that, right? So you will have a resistive force coming, and this is called the bending moment. So the resistance coming from the moment, usually we call it as bending moment. So this actually, it's better you all. I think you'll be. I hope you already know about the difference. I just want to clarify this. That's it. So let us go to the problem. We'll draw the initially. We'll just draw the free body diagram of this free body diagram. Sorry. Okay. Yeah. So I am just drawing the free body diagram. So this is my A. So this is my roller support, and this is 40 kilonewton meter. Sorry, this is a line diagram. Sorry, I am mistaken. This is not a free body diagram. This is a line diagram. So this is 80 kilonewton load. So can anybody just work out and tell me what is AX and AY? Meanwhile, I'll also keep working out, but you just maybe you can also do that. So what are the support reactions? Or at A we'll have two support reactions because this is pin support. So I'll just tell you what is a pin support. So this is a pin support. It can just rotate, but if you are trying to push it in this way, this will resist. So that means you have a resistance coming in X direction, and also if you are trying to press this in this way, you'll also have resistance in this direction. So this is a pin support. I'll say this as AY. So okay, I think this is X direction and this is Y direction, and this is AX. And let me call this as C. Okay, this is C. Let me call it as CY. I don't have any C X direction because it's a roller. If I give some load, let us say I'm giving some load, this will just keep moving this way. There is nothing to resist in X direction. So can anyone tell me the answers, please? Option B. Sure. Let me check this. So this is 80 and this is 45 and this is 45. So this is acting in this at this point, right? So I just transfer. I just do this force. So in this way. So this is 80 cos 40 is 1 by root 2. 80 sin 40 is 1 by root 2. Yeah. Did anyone get the same answer? Okay. Okay. Just I'll just do for the sake of others. So 80 by root 2. How much is 80 by root 2? Yeah. So this is 56.6 kilonewtons. Let us just clarify what is in X direction. So we have three equations of equilibrium. First one is sigma fx is equal to 0. Second equation is sigma fy is equal to 0. Third one is moment is equal to 0. Okay. In fx direction, let us take right side as positive and top as positive. Okay. So ax is in positive direction, minus we have 80 by root 2, and that's it, 0. So someone just join. Yeah, so ax is 56.6 kilonewton. So how do you find ay? What I'll do is I'll just yeah, I can just take moment about this point, right? So I'll take just moment about this point. Why do we take moment about this point? Because I don't know cy. So instead of knowing all these things, you just take moment about this point. You only have ay as unknown. Only have ay as unknown, right? Yeah, someone want to say something? Yeah, ay in. Someone is trying to say something. Yeah, okay. Sorry. So we'll have ay into times 14. So this is the lever arm, okay, minus what is the other one? 80 by root 2 into how much is this? 4. And can anyone say, do we need to consider 40 kilonewton meter in this? We have the moment, right? Do we need to consider that? Can anyone? Yeah. So we also have this, which is coming in this direction. How much is that? So this is in this direction, it is rotating in this direction, and this is in this direction, and this is again in this direction. So same, so plus 40, that is equal to 0. So how much you are getting? Yeah, yeah, I think everyone is getting this answer, B. Yeah. Anyone has any doubt, any clarification on this, or any clarification on bending moment or moment differences and force and shear force difference? Is it fine? Shall I go to the next problem? Okay. Yeah, this is again the similar kind of problem. Let us just find out what are the reaction forces for this. So this problem, uh, this is a hinge. Okay, this is a hinge support, and this is a roller support. So why I actually choose this problem is, you can see this is an I section. Okay, I section is something like this. Sorry, actually, this I'm not able to draw it very properly, but this is an I section. They are just this I section, this I beam, whichever you can see here, right? It is just placed on another I beam which is running into the screen, right? So this is just placed on it. That means it is kind of a roller. It can expand in this direction. It can expand in this direction. So it can also expand in this direction. It can just go in this direction. There is no restraint. You have only the restraint coming from this direction. So in this you have two different reactions. You have this reaction and this reaction. Okay. So uh, you again how do you find this angle? It's already given here. So this is 1.2, this height is 1.2, and this is zero point 0.9. So this is something like this. It is something like this. This is 1.2 and this is zero point 0.9, right? So this is like 3, yeah, this is 3, this is 4, and this is 5, something like that. So meanwhile you can also keep you can also keep finding out what is the reaction. I'll also try to find out. Okay, so I'm just drawing the line diagram of this. So the beam is something like this. Yeah, okay. So I have a beam something like this, and it is inclined in this direction. So this is my pin support, and this is my roller support. Okay, so if I just remove my uh, the supports, and then if I just draw the reaction force, it becomes a free body diagram, right? And I also have a uniform UDL. So usually this is easy to draw, so that's why I'm just representing the UDL as something like this. So this is 7.5 kilonewton per meter, and this is B, and this is A. Okay, so how do you find the components of this? The components will be something like this. So let us say this is by, and this is bx, the components, just for the sake of anyways, this components I'm just writing just for the sake of calculating all the moments. Okay, this is one component and this is another component of the same thing, by and bx. So maybe you can work out and you can tell me. Meanwhile, I'll keep working this out. So what shall we do first? So let us just initially, what we can do. Yeah, you can follow whatever you want. So let us say I have sigma fx0, sigma fy equal to 0, and also moment about that should be 0. Sigma fx, the summation of forces in x direction to be 0, then let us say this is ax, this is ay, you have the same thing bx and by. So we have a lot of stuff. So by I can write it as by can be written as, yeah, or else we can just say b times, so this is by, right? So this is 1.2, this is 0.9, how much this should be? Otherwise the same thing, you can proportionately cut it down. You can write this as 4 times, this is 3 times, and this will be 5 times. You're able to understand this, right? This is actually 3 4 5. This is the hypotenuse, this is the hypotenuse. You have, this is 0.9 and this is 1.2. This is, let us say, u divided by 3, everything u divided by 3. So this should be uh, this is like 3 divided by 3, this is 0.4, and this should be zero point 0.5 actually. I mean 0.5 times something. So 0.5 times, that is like 1.5. I think this should be 1.5. Can someone check whether this is 1.5? Anyways, this is how it is. So I think you can solve this thing right from now. It is easy to solve. You have ay, and this is ax. So you have b here, and what you need to do is you need to find the moment at point, I mean the support a should be 0, and the moment at b also is 0. Okay, the moment at b is 0. With, if you take the moment at b 0, then you'll have ax times so you have let us say ax is in this direction and b is somewhere here. So what is the lever arm? This is the lever arm. So you have lever arm of 1.2. So ax times 1.2. And how is this rotating? It is rotating in this direction. So is it something like this? So ax times 1.2, and ay is rotating in anti-clock, in clockwise direction, minus. So ay into, let us say, 2.9. And what about the load? 7.5 kilonewtons. So 7.5 kilonewtons is acting in this direction, and where is the centroid of the load acting? That is from 1 meter from the left support. So let us say, what is the total load acting? Minus 7.5 into 2 is the total load. Okay, into what is the lever arm? If this is 1, the total is 2.9, it is 1.9. This is equal to 0. This is equation 1. Okay, next, this is sorry. Sure, definitely, yeah, sure. So you have horizontal support at this point, right? You have an horizontal support reaction coming from support A. You have vertical support coming from support A. So what happens is that, let us say I'm just drawing a horizontal line from support B. I am just drawing a vertical line from support B. So what do we what do we know about support B? At support B, the moment should be zero because it is a roller. It can rotate here. The rotations about this point should be zero because it can't take any bending moment. That's what I mean, right? It can't take any bending moment. So the summation of moments at this point should be zero. So due to the reactions at B, let us say I have a reaction force coming at B. So B will have B is passing, the reactions are passing through the B, right? Just a second, someone joined, I think. Yeah. So when the reaction force is actually going through the point B, there is no, what is moment? Moment is force into force times, yeah, force times distance, right? Moment is force times distance. So you have force, but distance is zero there because it is passing through that point itself. So there is no moment acting on it. So that's why the reaction force at B times the distance is zero there. So that's why I didn't consider in this equation. Okay, that is clear, I think. So now when it comes to the other forces, what are the other forces I have? One is the load coming. This is the load which is coming onto the beam, and the reactions on the beam. The reactions at the support A. So I have horizontal reaction coming at the support A, and also I have a vertical reaction coming at the support AY. So what I'll do is at this support I'm having one force which is in this direction. This is AX. Okay. So this is the force. If I want to find the moment at this, how do I find? Force times the lever arm. So lever arm is actually the point. Correct. Correct. Exactly. So this is the perpendicular distance, right? So what is this distance? This distance is 1.2. So AX times 1.2. And how is this acting? So this is in this direction and this is in this direction. So it is acting in this direction. The what is it? F cross D is actually a vector notation. So F cross D. So you have it is acting in anti-clockwise direction. So in this example, I'm taking anti-clockwise as positive. So we need to be consistent, right? So for this example, I'm taking anti-clockwise as positive. So AX cross 1.2. Okay, this is due to the horizontal movement, and we have a vertical support. This is a vertical support. This is support reaction AY. So again, what is the perpendicular distance? This is the perpendicular distance. Right, you're right. So this is 2.9, and this is actually, and again, this is force, and yeah, this is displacement. So this is in this direction. This is force, and this is the displacement or the distance. So this is in this direction. So that's why I have written as AY into 2.9. And now let us come to this UDL. So UDL, you have this. So UDL is actually a kind of a funny thing. So how do we find the UDL is acting about for a length of about 2 meters, and the UDL is about 7.5 kilonewton per meter. So first, initially for these things, it is just a load. This is a point load kind of thing. So you have the load coming and the distance is D. But for the UDL, what you need to do is first you need to find the resultant load of this. So usually the resultant load is somewhere in the middle, exactly in the middle, because this is UDL. So the resultant load will be 7.5 times the given length. It is 7.5 kilonewton per meter, right? Per meter, about 7.5 kilonewton is acting. So to the for the full length, it is like 7.5 times 2. Okay, so that is what I have written. This is actually the resultant force. So most of the people, what they usually get confused in this actually. So what happens is that they'll take this as a point load. It is not point load. It is the resultant of UDL acting at that point. Okay, that is the resultant of the UDL. So this is 7.5 times 2. This is 7.5 times 2, and now the load is here. And what is the perpendicular distance? 1.9. So this is 1.9. So that is equal to 0. So now I hope now it is clear. Yeah. Okay. Thank you. So what about the other one? Now I have taken all these things. Fine. This is all set. All good. So I have one more equation. What is that equation? Moment at now moment at A is also 0, right? So moment at A is equal to 0. How do I calculate that moment at A equal to 0? That is again a task, right? Again, I need to find out how to calculate the moment at 0. So I have either you can do two things. One, let us say you have this, and if you have this, and if you know this distance, this is a perpendicular distance, right? You can directly say b, whatever the b you are getting, b times this d will be some moment coming here, and you have this, but we don't know about this again, we need to do a lot of geometry for this. Okay, so we, instead of knowing that, what I'll do is, instead of knowing that thing, I know horizontal and vertical things, right? So this is b times, what is this, 4 by 5, and this is b times 3 by 5. So I'll just tell you how I got this, b times 4 by 5 and b times 3 by 5. So what is the angle? So you have this is some angle, this is theta angle. What is this theta? Theta is equal to tan inverse of what is it, 1.2 by 0.9. So I think this is about 53 degrees or something like that. Instead of, yeah, okay, thanks. So this is about 53 something. So you can just make this, this will be theta, so b times cos theta, and this is b times sin theta, that's it. So if you do that way, this is actually kind of a generate, this is most common, you'll get this type of see, this is 1.2, then this should be 1.5, the hypotenuse, this is about 345, this is 3, this is 4, then this will be 5. So 5 square is equal to 4 square plus 3 square, something like that. Just a minute, someone, I think, no, just that's fine. I don't know whether I can help it. No. Yeah, anyways, okay. So this is how it is. So we have bx, we have by. Yeah, so b times 4 by 5. This is by. So now I think now I expect you to tell me about what is happening at moment at a. So I have b into 4 by 5 is this vertical component, and b times 3 by 5 is horizontal component. So tell me what is the moment at a? Can someone please tell me what is it? B times 4 by 5 times what is it? What is the lever arm? Right here. Okay, 2.9, and this is actually in this direction, right? So you can see the point is here, and the force is acting in this direction. So it is just rotating in this direction, just trying to rotate the support B in this direction. So yeah, okay. Next, what about the other one? I'm just writing it as minus, and I don't know whether it's minus or not. Let us see what happens. B times 3 by 5 times what is this? The horizontal component. Yeah, it's 1.2. And is it plus or minus? Is it anti-clockwise or it is clockwise? Okay, just see here. So this is the beam. I have, this is b times 4 by 5. Okay, and one more thing is, this is b times 3 by 5. Okay, so this is my point. Okay, so let us just say this thing, the load which is going upwards, right? This is trying to rotate this point in this direction. You can just imagine, see, this is here, you have force coming, and this is d, so you have force coming in this way. It is trying to rotate in this direction, so it is rotating in this, maybe for you it is in opposite direction, but you can also imagine what's happening. So it is trying to rotate in this direction, so in this direction, so that means it is trying to rotate in anti-clockwise direction. Similarly, let us say this we have. So you again, this is something like this. So you have vertical force coming, and this is the d, and it is again trying to rotate in the similar fashion. It's trying to rotate in the same similar fashion. So both are actually the same. It's the same sign. That's what I meant. So this should be also positive. If I'm taking this as positive, this is also positive. Now tell me about this. Tell me about this. What is this doing? This uh, this load 7.5 kilonewton per meter. Again, that is 7.5 times 2. That is the resultant force is 15 kilonewton, which is acting 1 meter from the support A. So what is this doing? What should I write for that? Is it minus or plus? Yeah, correct. Yeah. So this is 15 times 1. So that is 0. So can anybody find what is B quickly? No, I mean in this equation the only unknown is B. So what is B? 4 divided by 5. How much is it? I'm getting something around 4.93. Can someone confirm whether it's correct or not? Okay, thank you. So everybody's getting that answer, right? And everybody's able to follow it, right? The notations and all. Yeah, I'll take that as an yes. So what about that? So now we got B, right? So you can easily find what is by and what is bx. So what is by? By is again b times 4 by 5, and bx is b times 3 by 5. With this, what you can do simply you know ax plus bx is equal to 0. This is fx equal to 0, right? And summation fy is equal to 0. So with this you can find ax and ay. Shall I solve that, or you can solve ax and ay? I can solve. Actually, you can tell me if you want me to solve. I can solve it, because we are still in. It's fine. Okay, yeah. Okay. Thank you. So B, you got it. Ax and ay you can just find out by uh, a force equilibrium, right? Now coming to the next question. Yeah, you can see this question. So in this question, what there are what it is asked is, determine the shear force and the bending moment in the beam below at a distance of x from the fixed end. So this is the fixed end. So let us just draw the line diagram of this fixed end. This is how usually we denote the fixed end, and this is the triangular load. Sorry, yeah, this is the triangular load. So this is 2 kilonewton per meter. So here it obviously it's triangular, right? So it obviously means that it is 0 here, and it linearly increased to 2 kilonewton meter, and this is a very big cantilever. 30 meters is like you get, it is very huge. You just imagine how big it is. So it's a very usually we use this kind of cantilevers. You can see that in the balconies, and in kind of a canopy structures, or you can also find this kind of things in parking lots. So 30 meters is like very huge actually. So you have to maybe the design should be very rigorous for this. We will have a very huge section coming from this. Okay, fine. Okay, so let us calculate what is the shear force coming from, because of determine the shear force and bending moment. So yeah, it is asking me to actually draw the shear force diagram and bending moment diagram. That's what the question is. So Can someone quickly say what are the reaction forces? Reaction forces, please. Let us call this as support A, and this is the end of the beam is B. Yeah. Yes. Yeah. Yeah. Correct. So A by AX, and we'll also have a moment. Let it. It is moment at A, but it is actually the bending moment. Okay. So moment at A. So what is AX? What I can do is instead of directly saying just AX, I'll take a force equilibrium. Just assume this as triangular load. So Fy is equal to 0, sigma Fy is 0, Ax plus, now tell me how to calculate the triangular load, like what is the resultant triangular load. So so far we have seen for the rectangular load, the resultant of the force is the given load multiplied by area, right? Oh, sorry, multiplied by the length. So for the triangular load, for the linearly varying load, it's what usually it's what technically it's called. So the linearly varying load, LVL. So uh, what should be the resultant force? Can someone say? Yeah, area of triangle. So what is the area of the triangle? Half into the length of the yeah. Yes, yeah, yeah. So 30 into 2. So this is what the area, and this is the resultant force. Okay. So where is the resultant force acting? So in the triangular load, in the rectangular load, what we have done is the resultant, it is acting right at the middle, right? So if this should be a by 2, this should be a by 2. So what about for the triangular load? Yeah. So it will be acting at the center of gravity of it, right? That's what the concept is all about. So it usually acts at the center of gravity of the given load. So the center of gravity of the load is something like this. So something like this. So this is 1/3 length, and this is 2/3 the length, 2/3 of L, and this is 1/3 of L. So this is how it is. And can someone say when do we have linearly varying loads? What are the different scenarios where we'll have linearly varying load? So most of you are from, I think, BTech second year or third year, something like that. So uh, can you say one place or one scenario or one situation where you'll have linearly varying loads? Bridge. Bridge has actually a lot of members, right? You have the slab. You have, which part of the bridge you are talking about? You have girders. You have columns. You have piers. Uh, you have a lot of things on the bridge, right? Yeah, bridge. Yeah, correct. So usually for the earth retaining structures, right? Let us say you have an retaining wall which is retaining some earth here. Okay, so you want to construct a wall, and this is like a cellar. Let us say this is a cellar. So this completely is a cellar, and you have a retaining wall here. So usually cellar are underground things, right? Usually we have an underground thing for that. So usually in this case, what happens? It is always assumed as it is not assumed, usually it is actually a linearly varying load, because you can see here you have this weight only acting, and here there is no weight coming on the top, and as you go down you have lot of weight piling up, right? So this will actually be higher and higher. Similarly for the dams also, let us say this is a dam, and or a reservoir or something. So you have this water coming, so this will be something like this. So right, you always know what is the pressure at this point. Let us say the pressure at this point is, what is it? Rho times G into H. So as you go down, rho times G into H is H keeps on increasing. Rho into G is always the same. H keeps on increasing. How it keeps increasing? Linearly. You go step by step, it keeps on increasing. So that's how, that is where that is one of the place where we'll have uh, the linearly values. Anyways, so this is 0. So what is AX? AX is minus 30 kilonewtons. So minus, again, basically, yeah, again, I don't want to I don't want to make you any, I don't want to confuse you here. So AX, I have taken top as positive. In this, it is down, right? So here I should have considered negative. So in this way, I'll get AX as positive. Okay, this is positive, this is negative. So this resultant force is negative in the negative direction. So AX is negative. What about AY? AY, let us say in Fx direction, the equation of equilibrium is 0. So sorry, is it A? Sorry. Okay, so this is AX and this is AY. I'm sorry. So AY is 30. And what about AX? AX plus, do I have any other load coming in horizontal direction? In horizontal direction, do I have any other load, external load? This is vertical. No, right? So there is no other load. So the AX plus 0 is equal to 0. That means AX should be 0. So I don't have any horizontal load coming. And what about that? What about MA? MA can be found out as MA plus AY into what is the distance of AY, and acting, it is acting at the point A itself. So AY into 0 plus AX into 0 minus the resultant force is 30 kilonewtons. So this is 30 kilonewtons, and it is acting at a distance of, how much is this distance? It is two thirds of 30, and that is 10 20. Yeah, it is 20. So what is MA? 600 kilonewton meter. 600 kilonewton meter is a very huge force, actually, a very huge moment demand. That that itself, this is because, again, it's not because of the load. Load is 2 kilonewton per meter itself. The maximum is 2 kilonewton, but the lever arm is too high. Like, it's very huge, 30 meters. So that is the reason why you are getting a moment demand of about 60 kilonewton meter there. So now, let us just write down the shear force equation. Okay, so what I'll do is I'll just draw a free body diagram. This is 30. Okay, and I have this. Now let us say at position X, I'm taking this section, only this part. At position at some location X from a support A, let us call this as V. Okay, this is V. So sigma Fy is equal to 0. So what is sigma Fy? So V positive plus 30 is positive minus, what is the resultant of this triangular area? So if it is X, for 30 meters, this is 2. For X, how much is this? So let us say for 30, you'll have, this is 2. So what is the slope? You have slope is 2 by 30. That is 1 by 15. So 1 by 15 times X. Okay, is it fine? Is it clear? So this will be 1 by 15 times X. Let us just substitute and check. What if the X is 30? For X equal to 30, it is 2. That's what it is. So what is the area? Half times 1 by 15 times X into, you have X again. Fine. So what is V? I'll just write down in the next slide. So V plus 30 minus 1 by 2 times 1 by 15 times, what is it? 1 by 15 times X into X. I hope this is what I've written. V plus 30 minus 1 by 2 times 1 by 15 times X into X. How much is this? V plus 30 minus X square by 30. Can anyone solve this and tell me? 1 by 30 is like 0.00, yeah. V plus, that is V plus, yeah, that should be equal to 0 because sigma Fy is equal to 0. V plus 30 minus 0.03 x square is equal to 30. That implies V is equal to minus 30 plus 0.033 x square. Minus 30, yeah, minus 30 plus 0.033 x square. So what we have assumed is V in the positive direction. What if the V is in the other direction? If we assume V as in this direction, in V positive in this direction, then we'll have a reverse of the symbols, right? This 30 minus 0.033 x square. So one thing which you always keep in the mind is, see, in this like, okay, which one is matching? Let us say, let us consider this equation itself. V is equal to minus 30 plus 0.033 x square. This is what we got, right? Let us stick on to this. So due to the shear force, we have considered it as minus 30, and due to the load it is 0.033 x square which we got. So just see, this you always mention what you have actually represented. In this you have represented positive as the top, right? If it is going, if it is upwards you have taken it as positive. If it is downward, you are taken it as negative. Now you see here, in these equations you can see it is 30 minus 6. So you have this thing. So I hope you are able to understand. If you are taking V as negative, you will get 30 minus 0.033 x square. Okay, let us say it is a shear force equation. What about the bending moment equation? You already have M coming here, and you have V in this direction. Okay, and you have this thing again coming here. This is 1 by 15 times x, and this is x. So can you tell me what is uh, M at x? Mx. Now I'm taking anti-clockwise as a positive. So Mx minus, so you have V in this direction and D in this direction, so it is rotating in this direction. This force, what is this is AY. So AY is actually making this section to rotate in this direction, in clockwise direction. So this is minus 30 into X. Okay, and you have bending moment which is coming, and this is in, what is this is anti-clockwise direction. So this is plus, right, because it is in the same direction of Mx, plus, what is M? This is 600. I think it's 600. Yeah, it is 600. That is equal to, did I miss something else? Yeah. You can call it as UVL, okay? Uniformly varying load or linearly varying load. UDL is uniformly distributed load. So yeah, so UDL, again you have resultant acting in this direction, and it is actually making the section rotate in. I mean this section rotate in anti-clockwise direction. So what we are taking anti-clockwise as positive. So positive. What is the resultant? A half times 1 by 15 times x square. What about this distance? This is 1 by 3 times x. Okay, so that should be equal to 0. Mx minus 30x plus 600 plus this is 1 by 90. Is it 90? 15 to 30, 33 is here. 90, and this is x cube is equal to 0. So divided by 90, 0.011. So mx is equal to minus 600 plus 30x. Is it minus? Yeah, minus 0.011 x cube. Okay, this is mx. So let us just clarify. Minus 600 plus 30x minus, yeah. So what is the right answer? This is the right answer. Okay, any doubts in this? Any doubts? You want some clarification? One addition I just want to tell you is, why do we need to calculate mx, right? So what's happening at mx? See, mx is actually unknown, right? It is unknown. So what happens is that if you want to let us say you have you want to design something. Let us say you want to design a beam, maybe the beam which you are just you know which is lying right above the place which you are where you are sitting. If you want to design that beam, you actually wanted to know what is the bending moment coming in the beam, what is the shear force coming, and if torsion, if suppose you are also having some torsion, you want to find out. Because if you have these things, these are the inputs for your designs. So what structural analysis gives you is that it will give you what are the inputs you want for the design. So you'll analyze it, you'll find out the bending moment demand coming, the maximum bending moment, the maximum shear force, the maximum torsion which you are getting. So from that you usually find out the sections which you require for the beam. So what should be the size of the beam, what should be the quantity of the steel required, so on and so forth. So I hope this is clear. This problem is clear, right? Is it fine? You are able to understand this? Okay. So let us just go to the next one. This let me check. Let me check if I have any interesting questions. Let us solve this frame. Okay. Let us solve this frame first. So this is frame. Okay. You have supports in two different in y levels. So two different y levels, and you have a beam, and it's all you also have a column. It's a vertical member, right? So usually columns are the vertical members. So we have a column and also we have a beam. Like I said before, this is again a roller support, okay, and this is a pin support. So right now you don't you no need to worry about this, how to define these supports. You usually in the question it's always written. So here I am actually I did not mention, I did not completely copy the question. So and usually in the question they'll be mentioning it, what is it actually. Is it a roller support or is it a, yeah, is it a roller support or it's a pin support? It's always mentioned in the question. So I'm just trying to draw the, yeah. So we have a roller support here, okay, and we have a pin support here. So we have 5 kilonewton load acting this place, and we have 8 kilonewton load acting at this place. Let us, okay, it's already named A, this is B, and this is C. So maybe you just keep this in mind. Usually for an I beam, right? You know the I sections. Maybe you might have seen a lot of I sections in steel structures. So let us say this is a steel structure. You have seen a lot of I sections. So for a steel structure, when you are making any connection, only the web. See, this is called the web. This is web. This is web, and these are called flanges. Let us say this is top flange and this is bottom flange. This is bottom flange and this is top flange. So you can see in this figure, when only the web is connected, when only the web is connected, and in this when only web is connected, that means so if web is only connected to any of the other section coming. So if only web is connected and there's no connection with the flanges, that usually actually means that it is a hinge connection. Okay, it's a hinge connection. So if the flanges are also connected, that means it can also transfer moment. If it can transfer moment, that means it's a fixed connection. It's a rigid connection. So in this you can see web and the flanges. So in this, that both the flanges are connected, and also in this the webs are connected. The web and flanges are also connected. So this can actually support, this can also transfer the movements. So difference between rigid support and fixed support. Okay, now the question will come, what is a rigid support and what is a fixed support? So this is called a rigid support, okay, and this is called a fixed support. This is called a fixed support. For a fixed support, we'll have support reactions mx, sorry, vx, vy, and you'll also have bending moment. Rigid support also, you'll have all these things. You'll have you have vx, you have vy, you also have moment coming, but this can actually sway. You can it can go in this direction, it can just move here. Okay, when it rotates, right, like for example, if you are loading in this way, let us say this is the deformation or the deflection diagram. Okay, so what happens is that, yeah, this is in this direction, right? So it can, I'll just draw it here. Okay, please assume this as a straight line. Yeah. So you have a load coming here. So let us say, oh, how it deforms. It will deform something like this. Okay, and what is the perpendicular direction? This is the perpendicular direction. So this actually deforms in this direction. It deforms something like this. Okay, and what is the perpendicular? Yeah, this is, and this beam deforms in this direction. So this is the original beam and column, and this is the deformed shapes. I'm just drawing it a little thicker. This is the deformed shapes. So what I mean to say is, for in the rigid joint, it will also try to maintain that 90-degree, whatever the initial uh, angle it has, right? This is the 90-degree angle, so it will try to maintain 90-degree after the deformations also. But for the fixed support, it's not like that. It is fixed always. It will not move actually. It will always bend like this. It will be zero all the time. So that is the difference between rigid. Rigid, we can't say rigid support. Rigid is actually rigidity. You have beam and column joining. It's called a rigid joint. Basically, it's a joint actually. So it's basically a rigid. We'll call it as a rigid joint and fixed support. So now you can calculate now. So this is AY. You have, this is CY, and this is CX. Okay. So let us take moments about C as 0, because you have two quantities, two unknowns, and you have one unknown here. So can anyone quickly calculate what is AY? AY times 4, okay, minus 18 times 2, okay, and this minus 5 times 2 is equal to 0. AY, how much is this? 6.5 kilonewtons. I hope everyone is still there. Yeah, okay. Thank you. So AY is 6.5, right? So what about CY? So we have F sigma Fy 0. In Y direction, you have AY minus 8. What is this? Plus CY is equal to 0. So CY is 8 minus AY. That is 8 minus AY is 6.5. That is 1.5 kilonewtons. So we got CY. How do you find the CX? CX is very easy. Sigma Fx is equal to 0. Let us take rightward positive. Cx, what are the loads I have? Yeah, I have minus 5. Minus 5 is in your left direction, is equal to 0. Cx is 5 kilonewtons. So you already have the support reactions coming, right? So Cx and Cy and Ay, you have it. So once you have the support reactions, you can now draw a FBD, free body diagram. So this is 6.5, this is 8. Everything is actually in kilonewtons. This is 5, this is 1.5, and this is 5. Okay, is it fine? Can you draw bending moment diagram for this? Shall we draw the bending moment diagram for this? Yeah, let us draw the bending moment diagram for this. Okay. So now what I'll do is I'll just actually take those things separately. We have beam. So beams are actually horizontal members, right? Usually we have horizontal members, those are called beams. The vertical members, those are the columns. For the beams, the majority of the loads are bending moments. For the columns, the in addition to bending moments, we'll also have uh, a significant axial loads acting, axial forces acting. Okay, so this is 6.5 if I'm not wrong, 6.5, and this is 8. Okay, so now I have removed this support. That means I need to balance the forces. So this should be 1.5, right? And what is the moment? So this is 6.5 times. So you also have a moment generated because of this. So this is 6.5 times, which is this 4. 6.5 times 4 minus 8 times 2. 6.5 minus 8 times. This is 10. So this is in this direction. It should be resistant. So this is 10 kilonewton meter. So now what happens here? So Newton's third law, right? You have an equal and opposite reactions coming. So if this is on the top, this should be compressing. So this is 1.5 kilonewtons. If this is clockwise, and this should be anti-clockwise. So this is 10 kilonewton meter. Now what happens here? So if this is like this, and here you have 1.5 kilonewton coming, and if it is 10 kilonewton, you have this. How much is this? This is 5. If it is 10, actually there should be yeah, you have 5 coming like this. So 10, and how much is you should have 10 times, sorry, 10 plus sorry, 10 minus 5 into 2, that is 10, so that is 0. That is what we have done here. So it's a hinge support, right? It is a hinge here. So at the hinge, the moments are 0. So it is 0 here. So let us draw the bending moment for this beam member first. So this is the beam member. You have 6.5. Let us go with the shear force first. So at the face, it is 6.5 and it is constant. Let us take this section. Let us say this is x. So at x, it is constant. It will be constant. Let us say when it passes this section. Let us say this section. Let us look into this section. So at this section, you have 6.5 minus 8 coming down. So that is how much is it? Minus 1.5. So it should come down. It should come down. Sorry, it should come down like this. This is minus 1.5, and then after that it is again constant here. So it is constant. It is constant. Again you have a 1. Again you have 1.5. So this is for the beam. Okay. And what about the column? When it comes to the column, just a second. Yeah, when it comes to the column, there is no shear force here. Shear force is actually the one which is acting in this direction. So there's no shear force here, 0, 0, 0. And here you have a shear force in this direction. And when it comes down, the shear force here is again 0. So just below this point it is 0, just above this point it is 5. So this is 5 kilonewton shear force, and this is 1.5 kilonewton shear force. Here it is 6.5 kilonewton shear force. Okay, these are shear force diagrams. And what about the bending moment? So let us say at this point the bending moment is 0 because that's a roller support. So what about in x? So it is 6.5 times x. So this point is 6.5 times 2. This is 2, right? This is 6.5 and this is 2. So 6.5 times 2 is 13. So the bending moment here is 13. It is linearly varying because At this point, it is 6.5 times x. So it is something like y is equal to mx. So it's a linear curve. So at this point, it is 6.5 times x, and how much is this? This is 13. Now, what about the bending moment at this? This it is about 10 kilonewton meter. So 10 kilonewton meter, it um, is it positive or the negative? So we have 6.5 times x, which is 4 minus 8 times 2. Let us say this is mx. So how much is this? 6.5 times, that is 10. That is what it is. So here it should be 10. If this is 13 kilonewton meter, this is 10 kilonewton meter. Similarly for the column also. So you have 10 and here it is 0. That means you have 10 constant up to some point, and then you have, it will be 0 here. This is 10 kilonewton meter. This is 10 kilonewton meter. So you have constant bending moment at this point, and it is 0 here. Is it fine, or is it? You're able to follow this? Yeah. Okay. So this is about the bending moment diagrams. Will you draw bending moment? This is again a very simple problem. So let us just draw the bending moment diagram for a bending moment diagram and shear force diagram for this. Okay. I don't know why I'm not able to draw straight lines. So this is P. So you can just tell me what, like, if this is P, let us just solve this problem. So this is P. You don't have any you have reaction here. This is, let us say this is AX. So there is no AY because it's a roller support. So there is no, you'll have BX and this is BY. So BY is actually is equal to P because you should have a force equilibrium in y direction. This is P. Yeah, that is fine. That is all right. So what about the other one? So let us say, how do you find AX? So AX will be again a question. So uh, about, let us say the moment about A is equal to 0. So Bx times L, okay, Bx times L, this is in this direction. Bx is rotating A in anti-clockwise direction. I'll take it as positive. Uh, Plus By times 0. So By is actually passing through A. So there is no lever arm there. So it is 0 again. And what about this? This is rotating in the clockwise direction. So minus P times, what is this? L is equal to 0. So Bx is equal to P. That's what it is. Bx is equal to P. So when Bx is equal to P, Ax will be in this direction, it is P. Because you have force in x direction should be 0. So now I'll draw the free body diagrams. This is P, this is P, this is P again, this is P. Actually, this is one of the interesting problem you can see. So if you are applying a P load at one end of the cantilever, so you can just simply call this as a, this is a simply supported beam. You have a cantilever, on the beam on the beam, and then you have this P load acting. So you have load P acting here. You'll have a reaction. All the reactions are P. The main reason is actually the lever arm. You have the same length of the column and length of the beam. So for this, how do you find? the shear force diagram. So let us call this as column and this is beam. So this is beam, this is column. So for the column, what I'll do is, let us say this is a column. At point A, you have P shear force, and all through the points, let us say all these points, there is no load acting, there is no load acting, so it is constant. But when it comes to the point B, just before the point B it is P, just after this it is 0. So this is how it is. So it is P. This is the shear force diagram for the column. For the beam it is, at this point it is again, you go in this direction, in this direction, in this direction, in this direction. All the directions it's P. So the shear force is P, and the shear force is P itself here. Okay. So now the question is, uh, at this location what's happening? So shear force, usually you know that, right? Let us say that beam is having a cross section of this. This is a cross section of the beam. Okay. Usually the shear force is in this direction, right? You always take in this direction. So the vertical direction usually, right? So this is how it is. This is how the shear force is acting in the vertical direction. So we are actually finding out the tangential to the cross section area. So that is what the shear force here is. So when it comes to the bending moment, so this is column, this is beam. When it comes to the bending moment for the column, at point A, that is a roller support, the bending moment is 0. What about subsequent points? It is actually, this is actually rotating in this direction. So P times X, P times X, but now you need to be very careful. So let us say this is a beam. First let us talk about the beam. So you have P coming here, and this is a column. So that is why I actually asked you to draw this free body diagrams. So you have P here, you have P here, and this is P here. If you remove, you just bifurcate, or you just break down this complete frame as a column and a beam, it should have reaction coming from here. This is P, and if this is P, this is P by L, right? So this is rotating in this direction, the reaction will be in this direction. So this is P by L. So you will again have a reaction coming in this direction, and you will also have P coming in this direction. Okay. So for the column, initially it's 0, and it keeps increasing up to PL by 2. Here it is PL by 2, but at, at this point it is PL. So PL by 2 plus PL. So that is again PL by 2. And sorry, I'll draw it in another way. Yeah. So what I mean to say is, let us say this is the column, this is the beam. You have P load coming here. So you'll also have a reaction P here. If this is P and this is length L, you'll have a reaction moment, or the bending moment as PL, and the same PL you'll have in opposite direction here, because at the joint you should not, the sum of the moment should be 0, right? So uh, it's not the sum of the moment, it's actually the reaction, right? You have an action, the reaction should be the same. So it's PL, and if it is in the direction, this is in the downwards direction, upwards, and this is downwards, and you have P in this direction and you have P in this direction. So let us say this is A and this is B. So let us draw the bending moment of A and B. So at this, up to L by 2, this is L by 2, this is L by 2. So up to L by 2, it is actually linearly varying, P into L by 2. Okay. After L by 2, you have in this direction, and this is in this. So P into L by 2 minus, you have PL. Right, so PL by 2 minus PL, that is minus PL by 2, so you have a sudden jump here of PL. So this is PL by 2, and this is minus PL by 2. And from here onwards, what happens is that again it keeps going in a linear fashion, and it will be 0 here, because this support is a pin support, B support is a pin support. So now what's happening in the beam, that is what we also require. So at this place it is 0 because P into there is no lever arm here. So as we go here, the lever arm is increasing, at the same time the bending moment is also increasing, so it is linear. This is PL. So this is for the column, this is for the beam. So bending moment diagram. So is this clear? Like you're able to follow this bending moment diagram? Yeah. So let us. There are few more questions. I'll just maybe you can note it down and maybe you can try this. Uh, maybe yeah. I think only I have left. Yeah, this question is almost the this is the same as we have done. You know, similar to this question. Just a second. Yeah, this is similar to this question. So we have just a minute. I think yeah. So we have an overhang and we have a simply supported with an overhang. So similar to that, you can work out this question. The same thing. You have simply supported with an overhang, but for the simply supported, instead of a inclined load in the other question, we have UVL, uniformly varying load. Okay, can you try this, or shall I? Because it's already 8:56, so I don't think I can finish this question. So can you try this, or shall I give some clues, or you can try this question? Can someone respond? Sure, sure. Yeah, yeah. Yeah, you can tell me. Yeah. So right now, actually, I'm not. Yeah, you're right. I can say that. So right now, I'm not concerned about which is tension side and which is compression side, because that we can say when we are actually defining what is sagging and what is hogging. So I just want to, yeah. So for the column, usually what again that is about, like you said, it is about the tension side. So if I, you can see this is how let us say this is what my beam is, right? So how is this when I'm applying P load in this way, how the beam bends? It will bend in this direction, and this part will be like this part will be going in, sorry, this part will be going in this direction. You're able to follow this, you're able to follow the deformation profile or deformation diagram. If I'm bending, yeah, see, you have this and you have, is it in this direction? So I have load coming in this direction, and my this will be in this direction. So yeah, yeah, you're right. So this is in this direction, and this is in this direction. This is what you are mentioning, right? Yeah. Yes. Yeah. It's a rigid joint, so this 90 degrees has to be maintained. So yeah, this is wrong. Yeah. So usually, for example, if we have a cyclic load, like for example, instead of P being in this direction, which is downwards, let us say if I'm pulling in this direction also. So let us say I'm pulling, making this P in this direction also. So then it should be in this direction. So if the P is in bottom direction, this is how it goes. So when it is in this direction, what I'll do is I'll draw the minimum diagram in the tension side. So like you said, yeah, this should be in this direction, and this should be in this direction. Yeah, yeah. Point of, sorry. Yeah, but we also have AX coming here, right? You can see AX we have. Okay, so when we have AX times D, and also we have 7.5 times, let us say we have this thing, 7.5 times, what is it, 2 into D. So this we can make it as 0. This can be 0. You are able to follow this? Yeah, yeah, yeah. Yes, yes, you're right. That's what actually initially also I was mentioning that instead, like you can directly take this, like you said, if you know this D, right? What is it called? Uh, uh, Deliver arm. Yeah, we can directly do that also. Dy into this length, if you know that length as per the geometry, yes, you can definitely do that. So this length you can actually find out, right? Like for example, you just take like this, and this will be something like this. So you can find this length, right, with the geometry. Yeah. Yes. Yes, we can do that. Yes. Uh, yeah, you're right. Because I actually didn't follow that because we are always used to finding out bx and by, right? So we are always into vertical and horizontal components. So that's why I followed this thing. Otherwise, we can do that if we are fine with the geometry. I think yeah, that is a single straightforward step. You can directly get B, reaction B. Yeah. Yes. Yeah. Okay. So let us say, okay, let us just go by the mechanics. Okay. Let us just go by the mechanics. So what I'll take a new page. So this is how it is, right? Yeah. So let us say I have, what are the reactions I'll be getting? This is AY and this is AX. And here I'll have BY and this is Bx. These are the reaction forces. Okay. Let me what I'll do is I'll apply a horizontal force here. Just let us go with the mechanics itself, only the mechanics. If I apply a horizontal force, now how many equal like how do we solve this? So we have, four equations of equilibrium. Sorry, four unknown forces, four unknowns. We have three equations of equilibrium. So it should be uh, and also we have one extra equation. So four, we can solve. Let us say we have ax, ay, bx, by. Four unknowns means we need actually four equations to solve. So we have three equations. Let us what I'll write it as ax plus this force is F. Ax plus F plus bx is equal to 0, one equation. Ay plus by is equal to 0. This is one equation. And I'll also have, I'll take moment about this point. So all these things will vanish. Ax and Ay will vanish. And f into, I'll take this as d1, f times d1. Sorry. Okay, I'll take moment at this point as 0. So f will also be, f will also not participate. F bx into, let us say this as d1 plus by times, let us say this as d2 is equal to 0. So we have three equations, and one equation we are getting from the moment equation about this. So about this hinge, the moment should be 0, right? About the hinge, usually what is hinge, even in the truss systems we'll say that those are hinged connections. So at the hinge the moment should be 0. So for that what we'll do is ax times this distance, let us say this is a1, and that is 0 again obviously, and ay times a1 is 0. So we have 1 2 3 4 equations, we have 4 unknowns. So that is statically determinate, that is for sure, but your doubt is whether it is stable or not, right? Yeah. So when it comes to the stability, now when it comes to stability, let us just make a hinge here, and we have this, so here, and this is here. So now what happens is that you draw the free body diagrams. You have fx, sorry, this is ay and this is ax. You'll have ay and you have ax about this hinge, and hinge will transfer the same thing, whatever it is transferred to it. This is ax, ay, and this is ax, and this is ay, and also you'll have some moment here, and you will also have a moment this way, and this is ax and this is ay, and this will be bx, and this is, sorry, by and bx. So for example, if the system is a mechanism, if it is a mechanism, that means if the system is unstable, usually you have an extra degree of freedom and an extra equation to solve it. Right now if you see 4 plus 3 minus 1, it is 0. If usually degree of static determinacy is less than 0, if we call it as unstable system, right? So, but in this it is ds is equal to 0, so it has to be a stable system. Yeah. So even though if you have these moments, right? For I understand your doubt. Let us say you have this. For example, this is a pin support. If you say that you are giving some load here and everything is rotating, right? But the moment here is actually countering it. It is not allowing it to rotate. It's only transferring. So that is how the moment is being generated. But in other case, if you say that if this is something like this and you have something like this and you have a hinge here, then what happens, you just press this, it just simply go like this. That means it's forming a mechanism. This is completely an unstable system. Yeah, in this is completely an unstable system, but here you have a rigid support which is giving it's an extra thing. And also you also have again similar to again to answer your question, for example, if you have a roller support here, then again it is an unstable, because you can press this simply goes, it will move in this direction, it will rotate here, and it will just move in this direction. Yeah. Anyone have okay, yeah. So anybody have any other question, or you have any comments, or if you want to give some just yeah, if you have any